You are not supposed to see big, mature galaxies in a universe that is still a few 100 million years old, but that is exactly what James Webb is showing you. This far back, you expect small, faint systems just starting to form their first generations of stars. Instead, the telescope keeps picking up galaxies that look heavy, bright, and already busy, and that fact alone puts real pressure on the way you thought cosmic growth was supposed to work. Let's start with what these objects actually are, because the numbers themselves are already shocking. Astronomers talk about redshift, and they give it a number, Z. The higher the number, the earlier in the universe you're looking. With JWST, you're now seeing galaxies at redshift 10, 11, 12, even around 13. That means their light left them when the universe was only about 300 to 500 million years old, less than 5% of its current age. At that point, matter has barely had time to collapse, yet some already hold billions of solar masses in stars. The Milky Way has hundreds of billions of stars today, built up over more than 13 billion years. JWST is finding systems only a few 100 million years after the Big Bang that already seem to contain a large fraction of that kind of mass. You are seeing galaxies that on paper sit in the same mass range as today's big spirals, but they are appearing far earlier than standard models expected. This is why you hear people call them impossibly massive, not because they are literally forbidden, but because they are extremely hard to build in the short time available. So how did this even show up so fast, and why did it shock people who work on this every day? A big reason is deep survey programs designed for JWST. Two of the most important ones are SEERS, the Cosmic Evolution Early Release Science Survey, and JADES, the JWST Advanced Deep Extragalactic Survey. These are long, careful looks at small areas of sky. The idea was simple: count early galaxies, measure their brightness, and compare that to what simulations predicted before JWST launched. Instead, the data came back with more bright, red, early galaxies than expected. Here is the key point you need to keep in mind. It is not just one strange galaxy you can shrug off as a fluke. In fields like SEERS and JADES, you see a population. There are many candidates with high redshifts and high estimated masses. The universe is not giving you a single outlier, it is giving you a set of overgrown systems. That matters because theory is not just about what is possible, it is about how often something should happen. When your counts are off, and they are off by a lot at the bright end, the model is under real pressure. Now look at how fast these galaxies are forming stars, because the growth rate is where the tension really spikes. By splitting their light across different wavelengths, astronomers can estimate star formation rates. For many of these early systems, the numbers come out to tens, sometimes hundreds, of solar masses of new stars every year. Compare that to the Milky Way today, which converts maybe 1 or 2 solar masses of gas into stars per year. These young galaxies are running 10, 50, even 100 times faster in a universe that is still in its early stages. That speed is the core problem. In the standard cold dark matter picture, dark matter halos grow first, gas falls in, cools, and slowly turns into stars. You also include feedback, energy from young stars and supernova explosions, and from growing black holes, which heats and pushes gas out, slowing down star formation. In that framework, galaxies are supposed to gain their mass gradually. JWST is showing you systems that act like they skip the slow phase and jump straight into extreme growth mode. So what has to change for this to make sense? One option is that star formation in the early universe was more efficient than you assumed. Maybe gas at those times cooled faster, clumped more strongly, and turned into stars with less waste. Another option is that feedback was weaker or different, so gas was not blown out as easily, and galaxies could turn more of their fuel into stars before anything pushed back. Right now, simulations are being retuned to see if these kinds of changes are enough, or if even aggressive tweaks still cannot reach the masses JWST is suggesting. But there is another layer to this, and it is important if you want to be honest about the uncertainties. How sure are we that these galaxies really are as massive as they look? Most early JWST results estimate stellar masses using something called spectral energy distribution fitting, or SED fitting. You take the brightness of a galaxy in many filters, from shorter to longer wavelengths, and you compare that pattern to models of how stellar populations would shine. From that match, you infer how many stars are there, how old they might be, and how much dust is in the way. The catch is that dust and age can mimic each other, and that can confuse the result. Dust, made from heavy elements like carbon, silicon, and iron, absorbs blue light and lets more red and infrared light through. Old stars are also redder, so a younger, dusty galaxy can sometimes look similar to an older, more massive one with less dust. If you misjudge the dust, you can overestimate how much stellar mass there is. That is why some teams argue that part of the impossibly massive label might be an illusion created by these modelling uncertainties. However, even that more conservative view does not let you relax, because it just moves the problem. If you say, fine, these galaxies are less massive but dustier, then you have to explain how they produce so much dust so early. Dust does not appear out of nowhere. It is created in stars, especially in supernova explosions and the late stages of stellar evolution. To have a lot of dust by 300 to 500 million years after the Big Bang, you still need rapid, intense star formation and several generations of stars already living and dying. You still need the early universe to be busy, so you are left with a basic conclusion that is hard to escape. No matter how you tune the details, JWST is telling you that complexity in the universe ramps up fast. Either galaxies are forming stars and building mass much more quickly than your simple models predicted, or your understanding of dust, feedback, and early star formation is missing important pieces. In both cases, the early universe looks more active and more crowded than the old picture of a slow, gentle build-up. And this is only the part of the story where galaxies are a few 100 million years old. The tension jumps again when you ask a harder question. How far back can you push this? How close to the Big Bang can you go and still find galaxies? If you are already struggling to explain massive systems at 300 to 500 million years, what happens when JWST finds solid spectroscopic galaxies at even higher redshift, when the universe is younger than 300 million years and the first structures are already in place? If it already feels extreme to see big galaxies 300 to 500 million years after the Big Bang, what do you do when the telescope starts finding them even earlier? JWST isn't just seeing far, it's punching straight into the timeline, showing you galaxies that were already shining when the universe was younger than 300 million years. So what does that actually mean in numbers? When astronomers talk about redshift, they are basically telling you how much the light has been stretched by the expansion of the universe. Higher redshift, more stretch, earlier time. With JWST, surveys like JADES are now confirming galaxies with spectroscopic redshifts above 13, and candidates even higher. At redshift around 13, the universe is roughly 320 million years old. That is less than 1/4 billion years after the Big Bang, out of a total age today of about 13.8 billion years. In other words, you are catching galaxies in the first tiny slice of cosmic time where galaxies can exist at all. The key word there is confirmed. Early on, right after JWST started sending data, the community got flooded with claims of very high redshift galaxies, sometimes Z15, Z16, even beyond. But many of those were based only on what are called photometric redshifts. That means you look at how bright a galaxy is in different filters, you look at its overall colour pattern, and you let a computer match that pattern to a likely distance. It is fast and it works pretty well, but it is always a best guess, not direct measurement. This is why follow-up spectroscopy matters so much. With spectroscopy, you are no longer just looking at colours, you are spreading the light out into a detailed spectrum, and you are looking for specific features, sharp emission or absorption lines that get shifted to longer wavelengths by a very precise amount. Once you measure that shift, you have a hard number for the redshift, not just an estimate. You are not just guessing from broader colours, you are literally reading the fingerprints in each photon, and that is what turns a candidate early galaxy into a real, locked-in one. But how do you even find these things in the first place when they are so faint and so far and so stretched? One of the main tricks is called the Lyman break technique. In simple terms, early galaxies produce a lot of ultraviolet light, but the hydrogen gas between galaxies and around them can absorb photons above a certain energy. That creates a sharp drop in the galaxy's brightness at a specific wavelength. As the universe expands, that break gets pushed to longer and longer wavelengths. So observers use filters that cover different slices of the spectrum. A high-redshift galaxy will show up in some of the redder or infrared filters, but it will basically disappear in the bluer ones. That is why they are called dropout galaxies. They drop out of certain filters. JWST's NARCam instrument is designed exactly for this game. It has a set of near-infrared filters spaced so you can see where an object appears and where it vanishes. That pattern gives you an initial redshift guess, then spectroscopy comes in later to confirm or correct it. Now, step back for a second and think about what those redshifts really mean in distance and time. When you hear more than 13 billion light-years away, it is easy to let that phrase just slide by. A light-year is about 6 trillion miles. So 13 billion light-years is something like 80 quadrillion miles, tens of billions of trillions of miles. The photons JWST is catching left those galaxies long before Earth existed, long before the Sun existed, long before there was any solid ground anywhere. You are seeing those galaxies as they were when the universe was only a few 100 million years old. But the light has been on the road for more than 13 billion years. By the time that light finally hits JWST's mirrors, whole generations of stars and galaxies have come and gone. The Milky Way has formed, the Sun has formed, the solar system has formed, life has appeared on Earth, and only then does that ancient signal finally get recorded. When you look at one of those JWST deep fields, you are literally stacking thousands of those long journeys together in one frame. So where does this go next, and why are people talking about a race to the first galaxy? Because the title of highest redshift galaxy is not stable, it keeps changing. Every time JWST goes deeper, or a new survey finishes its analysis, there is a chance that the record will move. One group announces a galaxy at redshift 13, then another finds one at 13.2, then someone claims 14 based on photometry, then spectroscopy moves it down or confirms it, and the leaderboard shifts again. This sounds like a competition, and in a way it is, but it is also how the map of the early universe gets refined. Each confirmed galaxy at very high redshift tells you when stars and galaxies first turned on in large numbers. If JWST keeps finding robust galaxies at earlier and earlier times, the window between the Big Bang and the first light sources gets thinner. The history you used to spread over, say, the first billion years, gets compressed into the first few 100 million. That is why every new JWST cycle matters. It is another chance to squeeze the timeline of first light and see how extreme the early universe really was. And here is the part that raises the stakes even more. If you are already seeing confident, spectroscopically confirmed galaxies when the universe is a few 100 million years old, and if some of them already look surprisingly bright and built up, then you have to ask a harder question. What does that imply about the space around them? Was the early universe mostly empty with just a few of these? Or are we actually looking at crowded regions, early versions of galaxy clusters and dense structures forming way ahead of schedule? You probably grew up with the idea that the early universe was mostly empty, a huge dark volume with a few tiny galaxies slowly starting to appear. But that picture is not what JWST is giving you. Instead of a quiet, thinly populated cosmos, you're seeing something that looks more like crowded city blocks of galaxies, forming and packing together way earlier than anyone thought was reasonable. Start with the idea of proto-clusters. Today, in the nearby universe, you see giant galaxy clusters, hundreds or even thousands of galaxies bound together by gravity, filling regions millions of light years across. Those clusters had to come from somewhere They didn't just appear fully formed. Before JWST, you expected their ancestors, these proto-clusters, to be present at high redshift, but fairly rare and not yet very developed at very early times. Now JWST looks at regions at redshift greater than 7, when the universe is under 1 billion years old, and it's already finding groups of galaxies sitting close together in tiny patches of sky. You see several galaxies at almost the same redshift in the same small area, all unusually bright for their age. That combination, same distance, same region, similar extreme properties, is exactly what you expect if you're catching the early building stages of a future cluster. You're not seeing one lonely galaxy in a void. You're seeing several neighbours sharing the same gravitational well. That immediately raises a simple question. If structures like this already exist at such early times, what does the rest of the universe look like? And this is where galaxy number counts come in, and where things really start to clash with the old forecasts. Before JWST, you had models that predicted how many bright galaxies you should see at high redshift, like above 10, based on the standard cosmological model and on how fast dark matter halos should grow. Those models did allow some bright galaxies, but they kept the numbers low. Then JWST starts doing deep surveys, and you count the bright sources, and the counts are higher than many pre-JWST predictions, especially at the bright end. In simple terms, you are populating the early universe with way more light than you budgeted for. There are more luminous galaxies, and in some cases, they're more common than the models said they should be. You're not just off by a tiny margin in some ranges, you're significantly above the expected curve. That's already a problem if those galaxies were scattered evenly, but they are not. Some fields show clear overdensities, regions where galaxies clump more than average. That fits an idea you already had from simulations, the cosmic web. In those simulations, dark matter does not spread out smoothly. It forms filaments, sheets, and dense nodes, like a giant three-dimensional network. Gas falls into those dark matter structures, and galaxies form at the intersections, where the density is highest. What JWST is doing is giving you direct evidence that this web is not just a theory on a computer. At high redshift, you're already seeing what appear to be those intersections loaded with galaxies much earlier than you thought you'd be able to catch them. Instead of faint little seeds slowly growing, you see multiple galaxies that are already bright and actively forming stars, sitting right where the web should be densest. It means that by these early times, the skeleton of large-scale structure is already in working order, and it gets even more intense when you bring gravitational lensing into the picture. Some of JWST's deepest looks go through massive foreground clusters, programs similar in spirit to older Hubble efforts like the RELIX or GLASS Rodeo. Objects. Those big clusters act like natural telescopes because their gravity bends space-time. Light from even more distant background galaxies doesn't travel in straight lines, it gets bent around the cluster, stretched and magnified. You can think of it in very simple terms. You put a heavy ball on a stretchy sheet, the sheet dips, and anything rolling nearby will curve around that dip. In the real universe, mass is the ball, space-time is the sheet, and light is what's following the curves. JWST looks at a cluster, and behind it, thanks to lensing, you can see galaxies that would normally be too faint, too small, or too far away to detect. The lensing boosts their brightness and sometimes stretches them into arcs or multiple images. This matters for the crowded city idea because lensing is showing you that even in the far background, beyond those already massive clusters, there are more galaxies packed into tiny regions than you'd expect. The magnification lets you probe very small patches of the early universe in extreme detail, and what you find is not emptiness. You find more structure, more small galaxies, more candidates for early groups and proto-clusters. Lensing doesn't just give you a few extra dots, it reveals another layer of population you would have missed. So what does all of this mean for how structure forms in the universe? In the standard picture, you start with small fluctuations in density right after the Big Bang. Over time, gravity amplifies those fluctuations, making dense regions denser and empty regions emptier. That process is not instant. It takes time, and the timing is tightly linked to the properties of dark matter and the expansion of the universe. If JWST sees dense, bright, complex regions earlier than you planned for, it suggests that those initial fluctuations grew faster, or that matter was more efficient at collapsing into halos and forming stars than your simple recipes assumed. In practice, that means the scaffolding of the cosmic web seems to have been assembled faster and thicker than you signed off on. Simulations now have to push parameters, like star formation efficiency and feedback strength, to more extreme values to try to match the observed number of galaxies and the strength of overdensities. Some teams are exploring whether rare, high-density regions in the model could explain the data, while others ask whether you need to adjust deeper assumptions, like the properties of dark matter itself. No one has a final answer yet, but the pressure is real, and here's the key tension this sets up for the next step in the story. If you already have crowded regions full of galaxies, grouped into proto-clusters, shining hard and forming stars like crazy, then they are not just sitting there quietly. All of those stars are pumping out high-energy radiation, especially ultraviolet light, into the space around them. That radiation does something important to the universe. It starts to strip electrons off neutral hydrogen gas, changing the entire state of the intergalactic medium. So the natural next question is simple and sharp. If the early universe is this crowded and this bright, how did that change the fog that filled space, and how fast did the universe go from opaque to transparent? You're catching the universe in the act of turning the lights on, and it's not a calm, dimmer switch. It's a messy, fast, uneven transition, where whole regions flip from dark to glowing in a short amount of time. That's what reionization is, and JWST is letting you watch that change, not as a smooth global event, but as a patchy, chaotic process. To see why this matters, you need a quick reset of what the universe was doing right before this. After the Big Bang, things were hot and ionized, everything was a charged soup. As the universe expanded and cooled about 380,000 years after the Big Bang, protons and electrons combined into neutral hydrogen. That moment is called recombination. After that, for a long stretch, there were no stars, no galaxies, just neutral gas and dark matter. That era is often called the Dark Ages, because there were no strong light sources to light up space. Then gravity did its job. Gas fell into dark matter halos, the first stars formed, the first galaxies switched on, and the first black holes started feeding. These new light sources pumped out high-energy ultraviolet photons, strong enough to knock electrons off hydrogen atoms again. That process, turning neutral gas back into ionized gas, is what we call reionization. At some point, enough of these sources lit up that most of the hydrogen between galaxies became ionized, and the universe went from mostly opaque to mostly transparent to ultraviolet light. Now the question is, how do you measure that transition, especially at times you can't access with direct imaging alone? One of the key tools is a specific spectral line from hydrogen called Lyman alpha. When a hydrogen atom's electron drops from the second lowest energy level to the lowest one, it emits a photon at a very specific wavelength in the ultraviolet. In a galaxy, young hot stars create a lot of ionized hydrogen, which then recombines and can produce strong Lyman alpha emission. So if you take a spectrum of a distant galaxy and see a sharp Lyman alpha line, that tells you there is gas being lit up by star formation. The catch is that neutral hydrogen in the space around that galaxy is very good at scattering and absorbing Lyman alpha photons. If the intergalactic medium, the gas between galaxies, is still mostly neutral, Lyman alpha has a hard time escaping and reaching you. If the region around the galaxy has already been ionized, those photons can escape more easily. So when JWST takes spectra of galaxies at redshifts around 7 to 10 and looks for Lyman alpha, the presence or absence of that line tells you how neutral or ionized their surroundings are. What JWST is seeing points to a very uneven universe. In some sightlines, you see galaxies where Lyman alpha is strong, which suggests they sit in regions where the gas is already largely ionized. In others, at similar redshifts, the line is weak or missing, which points to more neutral environments. Put together, this tells you reionization did not flick on everywhere at once. Instead, there are ionized zones and neutral zones coexisting for a while. The picture that emerges is one of bubbles of transparency growing around groups of galaxies. A cluster of star-forming galaxies, maybe with some black holes mixed in, dumps out enough high-energy photons to ionize the gas in their local region, creating an ionized bubble. As more sources turn on and more bubbles grow and merge, a larger fraction of the universe becomes transparent to ultraviolet light. You're literally watching regions where intense radiation is burning through the surrounding hydrogen and clearing out lines of sight through a fogged-up universe. That brings up the obvious next question: who is doing most of the work here? Are normal young stars enough, or do you need more exotic contributors, like very massive early stars or actively feeding black holes? JWST helps here by letting you estimate the ionizing photon budget. From the star formation rate in a galaxy, you can estimate how many high-energy photons it produces per second. Roughly speaking, for every solar mass of stars formed per year, you get on the order of 10 to the 53rd ionizing photons every second, depending on the exact mix of stars. If galaxies are forming tens of solar masses worth of stars per year, that is an enormous number of ionizing photons. If the early stellar population is skewed toward very massive hot stars, sometimes called population 3-like stars, the photon output per unit star formation goes up even more. On top of that, if some of these galaxies host active galactic nuclei, with black holes accreting gas at high rates, those central engines also produce large amounts of ionizing radiation. JWST's spectra, which can separate the signatures of normal star formation from those of active black holes, let you test how much each component is contributing. When you add up the galaxy populations JWST is seeing, especially at redshifts above 7, you start to get a sense of whether they can account for reionization. You compare that to independent information from the cosmic microwave background, the leftover radiation from recombination. The microwave background tells you, through a quantity called optical depth, how many free electrons the photons scattered off on their way to us, which in turn reflects how long the universe has been ionized. Before JWST, many models assume that galaxies slowly ramped up their contribution and completed reionization by around redshift 6, with a fairly smooth evolution. JWST is now showing you that there are more galaxies, and sometimes more star formation, at earlier times than you expected. That means galaxies might be starting the job earlier and doing it more efficiently. The timeline starts to shift. Instead of a long, gentle reionization, you may be looking at something that begins earlier, accelerates faster and finishes in a more complex, patchy way. This is where the tension appears. If galaxies alone, with realistic assumptions about their photon output and how many photons escape into space, can drive reionization earlier and more aggressively than you thought, then your previous calmer picture has to change. If they can't, then you need to look harder at the contributions from rare, bright quasars, or at changes in the initial properties of early stars. Either way, the combination of JWST's galaxy counts, its Lyman alpha spectra, and the microwave background constraints is forcing you to redraw the curve of when and how the universe became transparent. And there's another consequence you can't ignore. If the universe is already being recognized strongly at these early times, that means there has to be a lot of star formation and a lot of stellar evolution happening quickly. That, in turn, means heavy elements and dust are being created earlier than you thought. Those metals and dust grains don't just change the chemistry inside galaxies, they change how galaxies look, how they cool, and how we estimate their masses. So the obvious next step is to ask, if you already have intense star formation and reionization this early, do you also have significant amounts of dust and heavy elements in place far ahead of schedule? Dust is the junk of dead stars, tiny grains of carbon, silicates and metals, and in a young universe you're not supposed to see much of it at all. A few 100 million years after the Big Bang, most stars haven't even had time to live and die yet. and yet JWST is already seeing dusty, chemically enriched galaxies at redshifts above 7, which means you're looking at systems that somehow ran through several cycles of star birth and death on fast forward. So what is JWST actually picking up here? One big clue is something astronomers call an infrared excess. When you look at a galaxy's brightness in different filters, you can compare what you see to what you'd expect from a dust-free population of stars. In some high-redshift galaxies, the infrared end of the spectrum is stronger than those simple models predict. That extra infrared light is a sign that dust grains are absorbing ultraviolet and visible light, heating up and then glowing in the infrared. At redshifts higher than 7, that means dust is already present when the universe is just a few 100 million years old. JWST is also finally showing you the rest frame optical and infrared features of these distant galaxies. Rest frame just means what the light looked like before the expansion of the universe stretched it. For nearby galaxies, you see those wavelengths directly with visible light. For very distant galaxies, the same features are shifted into the infrared, where instruments like NIRC AM and MIRI can pick them up. Some of the shapes and bumps in the spectrum simply cannot exist without heavier elements and dust grains. That tells you right away this isn't a clean hydrogen-only environment anymore. Then you go one level deeper and look at the actual chemical fingerprints. When JWST takes spectra of these galaxies, you don't just see a smooth rainbow, you see specific emission lines from elements like oxygen, nitrogen, and neon. The strengths and ratios of those lines let astronomers estimate something called metallicity. Basically, how much of the gas is made of elements heavier than helium. In the early universe, you'd expect those values to be very low, because all heavy elements have to be made inside stars. But JWST is finding galaxies, again at these very high redshifts, with metallicities that are not near zero. In some cases, they're a significant fraction of what you see in present-day galaxies. That means you are seeing chemistry that demands multiple generations of stars to have already lived and died. You can't get oxygen emission lines without massive stars fusing lighter elements into oxygen and then spreading it out when they explode. You can't get nitrogen and neon without similar processing over time. The basic message is simple. Heavy elements show up earlier and in higher amounts than you expected. So where does all this metal and dust come from? And how do you get so much of it so early? The main factories are two types of stars. First, you have massive stars that end their lives as core collapse supernovae. These stars live short, intense lives, sometimes only a few million years, then explode and throw newly formed heavy elements into space along with dust grains that condense in the cooling debris. Second, you have stars in a later evolutionary phase called asymptotic giant branch stars, slightly lower mass stars that lose their outer layers and produce dust and certain elements over longer timescales. To load a galaxy with dust by a few 100 million years after the Big Bang, you need both of these channels running hard. Massive stars provide a quick burst of metals and dust, but that still requires very high star formation rates early on. GB stars take longer to evolve, so if their contribution is important, the first generation of stars must have formed extremely early, almost as soon as gravity allowed gas to collapse. Either way, the picture is the same. Star formation and stellar evolution must have been highly accelerated compared to the slow, drawn-out history you might have imagined. Dust doesn't just change the chemistry story, it also changes what you see and what you miss. Dust grains are very good at absorbing ultraviolet and visible light. That means galaxies with a lot of dust can look fainter or redder than they really are in those wavelengths. Older telescopes like Hubble, which were mainly sensitive to visible and near ultraviolet light, could easily underestimate the amount of star formation happening in dusty regions or miss some dusty galaxies completely. But when dust absorbs that high-energy light, it doesn't just swallow it. It radiates the energy at longer wavelengths, in the infrared. That is where JWST's mid-infrared instrument, MIRI, becomes crucial. MIRI can see the glow of warm dust directly, even when the regions that produce it are heavily obscured in visible light. So JWST is not only confirming that dust exists early, it is also uncovering star formation that was effectively hidden from Hubble's view. Some of the missing star formation that you thought wasn't happening may simply have been hidden behind layers of dust. This has a big impact on how you think about the chemical evolution timeline of the universe. Before JWST, a common picture was that metallicities started out close to zero, then slowly climbed over billions of years as more stars lived and died, enriching the gas. You'd expect very metal-poor systems to dominate at high redshift, with only a slow build toward the richer compositions you see in the local universe. Now you have evidence that some galaxies reached relatively high metallicities much earlier than that smooth picture allows. If enrichment is this fast, then the periodic table in practice turns on much earlier across the cosmos. That has several consequences. Heavy elements change how gas cools, making it easier for gas clouds to collapse and form stars. Dust changes how radiation moves through galaxies, which can affect everything from star formation efficiency to how much ionizing light escapes into the intergalactic medium. Metals are also the raw material for rocky planets and complex chemistry, so pushing heavy elements earlier changes when, in principle, more complex structures, including planetary systems, can start to appear. All of this raises the stakes for your models. If galaxies can become dusty and chemically enriched so quickly, then the recipes you use for star formation, feedback, and chemical yields may be too conservative. You may be underestimating how violently and efficiently the first generations of stars processed their gas. You may also need to rethink the assumed initial mass function, the distribution of stellar masses at birth. If early star formation was biased toward more massive stars, you'd produce more metals and dust, and more ionizing radiation per unit mass of stars formed. And once you start talking about massive stars and fast enrichment, there's another piece of the puzzle you cannot ignore. Massive stars do not just make metals and dust, they also leave behind black holes. If the early universe is a place where gas turns into stars quickly, those stars live fast and die young, and chemical enrichment jumps ahead of schedule, then you have to ask, what does that do for black hole growth? How do you go from early star factories and metal-rich gas to the supermassive black holes that JWST is now seeing surprisingly early in cosmic history? You're seeing supermassive black holes already weighing millions to billions of times the Sun, in a universe that is still in its first few 100 million years, and that should immediately make you stop and ask, how did they get this huge, this fast? These objects are supposed to be the end result of long growth, not something that shows up almost as soon as galaxies exist. Yet JWST keeps finding signs that they were already in play very early on. The first clue comes from galaxies that don't just shine from their stars, they show signs of an active nucleus, an active galactic nucleus, or AGN. When JWST takes spectra of some high redshift galaxies, the light doesn't match what you'd expect from stars alone. You see broad emission lines, which come from gas moving at thousands of miles per second near something very compact. And you see high ionization lines, from atoms that have been stripped of many electrons by extremely energetic radiation. Those are classic signatures of gas spiraling into a black hole, heating up and glowing as it falls in. These AGN-like spectra at high redshift tell you there are already black holes actively accreting in the early universe, not just small ones, but ones pumping out enough energy to change the spectrum of an entire galaxy. In some cases, the contribution is strong enough that you can separate it from the surrounding star formation, and that lets you start estimating how massive the central black hole has to be to power what you're seeing. We already knew from earlier surveys, even before JWST, that quasars at redshift around 7 can host black holes with about 1 billion solar masses. That was already a major puzzle. Now JWST is pushing this issue into more normal-looking galaxies, not just the rare extreme quasars. You're seeing evidence that black holes of significant mass are sitting in galaxies that themselves are still very young, and that tightens the problem, because it means this isn't just one or two freak objects, it's part of the general early population. The growth timescale is where the numbers get uncomfortable. In the simplest picture, a black hole grows by feeding on gas, and there's a limit, called the Eddington limit, on how fast it can do that if the inflowing gas is in balance with the radiation pressure pushing outward. If you start with a small seed black hole and let it grow at that balanced rate, there's only so much mass it can reach by a given cosmic time. To hit 1 billion solar masses by a few hundred million years after the Big Bang, you either need to start with a much heavier seed, or you need to cheat that limit with episodes of super Eddington growth. That's why people talk so much about seed scenarios. One option is that the first black holes formed as the remnants of very massive metal-poor stars, sometimes called population 3 stars. Those stars might leave behind black holes with tens to maybe a few hundred times the mass of the Sun. If you start there, you need very fast, nearly continuous growth to get to the monsters JWST is hinting at. The other option is direct collapse, where a large gas cloud under the right conditions collapses into a black hole of 10,000 to 100,000 solar masses in one go, skipping the normal star phase. JWST doesn't see the very first seeds directly, but it does see their descendants and their host galaxies. When you see a young galaxy that already has a massive stellar component and signs of an actively accreting black hole that can lean you toward heavier initial seeds or extremely efficient early accretion. If galaxies that look only moderately massive already host surprisingly big black holes, that suggests the black hole got a serious head start. On the other hand, if you find black holes that are still relatively small for their hosts, it might mean you're catching them earlier in the growth curve. There is also the question of how tightly black holes and galaxies are linked this early. In the nearby universe, there are clear relationships between the mass of a galaxy's central black hole and the mass of its bulge, the dense central region of stars. Those relations suggest that black hole growth and galaxy growth are connected over long times. JWST is now starting to probe whether anything like that relation already exists at high redshift. In some systems, it looks like the central engine and its host are already roughly in sync with black hole mass and galaxy mass in the same ballpark ratios you see today. If that holds up, it means coevolution kicks in very early. The central black hole is not something that grows long after the galaxy forms. It is growing alongside the galaxy from the beginning. Gas that feeds star formation can also feed the black hole, and energy from the black hole can affect the gas that makes new stars. The feedback loop between the city of stars and the engine in the core is already running in a universe that is still very young. That leads to the last major question here. What is that feedback actually doing in these early systems? When a black hole accretes, it can launch winds and jets, driving gas out of the central regions. That feedback can quench star formation by blowing away or heating up the gas that would otherwise make new stars. In other environments, the same outflows can compress gas clouds and trigger new bursts of star formation. So AGN feedback can either shut things down or turbocharge them. JWST's spectra help you probe this by measuring line widths and shifts that trace how fast gas is moving and in which direction. If you see broad shifted lines that indicate gas flowing out at hundreds or thousands of miles per second, that's a sign of strong outflows. If those outflows line up with regions of suppressed star formation, you might be catching quenching in action. If instead they appear near intense starburst regions, you might be looking at a case where feedback is stirring the gas and helping it collapse in some places while clearing it out in others. Right now, the data suggests that many early galaxies with active black holes are in a highly dynamic state, with both strong star formation and powerful outflows happening at once. That combination makes it harder to say cleanly whether feedback is mostly shutting things down or mostly stirring them up, but it does tell you one thing clearly. The early universe is not separating black hole growth and star formation into neat separate phases. They're overlapping, competing, and interacting from the start. And if black holes and star formation are both running hard in compact, dense galaxies, you have to ask what the actual star-forming environments look like on the ground, inside those galaxies. How extreme are the conditions in the regions where new stars are born? How dense? How hot? How violent? JWST can't just count galaxies, it can zoom in far enough to show you what those early star factories are really like. The early universe is not a calm nursery, It's an overclocked star factory, and JWST is letting you step inside these places and see how extreme they really are. When you hear star-forming galaxy, you might picture something gentle, clouds slowly turning into stars over billions of years. What JWST is actually showing you is more like an industrial zone running flat out, where gas is being converted into new stars at a ridiculous rate in a very small space. Start with the basic numbers. Many of these early galaxies are forming tens to hundreds of solar masses of stars every year. That alone is already way above the Milky Way's current pace of 1 or 2 solar masses per year. But the really important part is where this is happening. These galaxies are tiny compared to the Milky Way, sometimes only a few thousand light years across, not the 100,000 light-year scale of our own disk. So you're cramming a Milky Way's worth of star formation, or more, into a region maybe 1/10 the size, sometimes even smaller. That's what astronomers mean when they talk about high star formation surface density. It's not only how many stars you make per year, it's how many you make per year per square light year of area. In these early galaxies, that number is off the charts compared to normal galaxies today. On the ground, inside those systems, that means gas clouds are extremely dense, pressures are high, and everything is happening close together. You're basically compressing whole galaxies' worth of stars into neighborhoods only a few thousand light years across. So what kind of stars come out of conditions like that? JWST helps answer that by looking at emission line ratios in the spectra of these galaxies. Certain pairs of lines, from oxygen, hydrogen, and other elements, let you estimate something called the ionization parameter, which tells you how intense the radiation field is around the gas. In many early star-forming galaxies, those ionization parameters are very high, meaning the gas is being bombarded by large numbers of high-energy photons. High ionization usually means you've got a lot of young, hot, massive stars. These are stars that are dozens of times the Sun's mass, with surface temperatures tens of thousands of degrees, blasting out ultraviolet radiation. When you see line ratios that demand that kind of hard radiation field, it suggests the stellar population is skewed toward massive stars, what astronomers call a top-heavy initial mass function. In plain language, for every pound of gas turned into stars, you're getting more big stars than you would in a typical galaxy today. That has big consequences. Massive stars live fast and die young. They pour out ionizing radiation, they drive strong winds during their lifetimes, and they end as powerful supernova explosions. So a top-heavy mix isn't just about making a lot of light, it's about creating a very hostile, very energetic environment. The regions where stars are forming aren't quiet clouds, they're being hammered by radiation and shockwaves almost as soon as new stars appear. Now, if you look at how these galaxies actually look in JWST images, their shapes match that intense story. They are not neat, thin disks with clean spiral arms. Instead, you see clumps, multiple bright knots, distorted tails, and warped outer regions. In many cases, it looks like several pieces are in the middle of merging. That tells you the early universe is not a peaceful growth phase where gas gently settles into disks. It's a crash and build zone where small galaxies constantly collide and combine to form bigger ones. Mergers do two important things at once. They disturb the gravitational field, which can drive gas toward the center of the combined galaxy, and they compress gas clouds, both of which can trigger intense bursts of star formation. So when you see clumpy, disturbed morphologies together with extreme star formation rates, it's a sign that frequent mergers are a normal part of life at those redshifts. The star factories are not just overclocked, they are being shaken constantly by collisions. But all this star formation and merging has a downside for the gas supply, and JWST sees that too. When those massive stars reach the end of their lives and explode as supernovae, they drive powerful winds. Spectra of some early galaxies show gas being pushed out at hundreds of kilometers per second, fast enough to escape the central regions and sometimes even leave the galaxy entirely. You see this in broadened and shifted emission and absorption lines, which tell you there's gas moving along the line of sight at high speeds. These supernova-driven winds are a feedback mechanism. They regulate how long an extreme starburst can last, because they can remove or heat the gas that fuels star formation. If too much gas is blown out, the starburst shuts down, at least until new gas falls in from outside. At the same time, those winds carry metals and energy into the surrounding intergalactic medium, enriching it and changing its temperature and ionization state. So the violence inside a single galaxy ends up affecting the space between galaxies as well. To understand how extreme this really is, it helps to compare to something closer to home. In the nearby universe, you do have starburst galaxies like M82, where star formation is much more intense than in the Milky Way. In those systems, you see strong winds, bright central regions, and high surface densities of star formation. They're already considered extreme by local standards. Now take that kind of environment and push it back to a time when the universe is only a few 100 million to 1 billion years old. Make the gas more abundant, the densities higher, and the radiation fields harder, and then multiply the intensity by a factor of several. That's basically what JWST is showing you. The most extreme star-forming regions you can find nearby are like small-scale previews of what early galaxies were doing on a wider scale. The early universe is full of compact, clumpy, high-pressure systems forming stars at rates that make even local starbursts look modest. You're not looking at a gentle ramp-up from nothing, you're looking at a phase where star formation, mergers and feedback are all happening at once at maximum speed. And that sets up a new question. If the small-scale environments are this extreme, what does that do to the overall shape and structure of these galaxies? Do they look like the well-ordered spirals and ellipticals you see today? Or does the visible structure lag behind the mass growth and the star formation? JWST is now resolving the shapes of early galaxies in detail, and what it finds is that many of them look messy and unfinished, even though in terms of mass and star formation history, they're already acting surprisingly mature. You've probably heard the simple story, galaxies start as formless blobs, then slowly settle into nice flat disks. Then some of those disks grow clean spiral arms over billions of years. JWST is basically telling you that timeline is way too neat. In the early universe, how a galaxy looks and how mature it actually is don't always match. You can have something that looks like a wreck, but under the chaos it's already holding a lot of mass and a long, complex star formation history. When you look at high-redshift galaxies with JWST's sharp resolution, you don't just see tiny round dots. You see clumps, chains and shapes people literally call tadpoles because they have a bright head and a trailing tail. You see multiple bright knots stuck together in one system, like someone glued several small galaxies side by side. At first glance, these objects look like unfinished pieces, like they're still being assembled and haven't settled into any final form. Here's the twist. Some of those clumpy chain-like systems are already massive. When you measure their stellar masses, they can rival or exceed the mass of normal galaxies you see in the nearby universe. Their spectra show not just a single burst of star formation, but evidence for stars of different ages, meaning they've been forming stars for hundreds of millions of years already. So you have galaxies that look like unstable piles of building blocks but are, in terms of mass and history, already well along in their evolution. So what happened to the slow story? The idea that galaxies need a lot of time to settle into nice disk shapes. JWST does see disk-like galaxies at fairly high redshift, so disks are definitely there earlier than we once thought. But a lot of the massive systems, the ones that already carry a huge amount of stellar mass, do not look like clean disks at all. They're lopsided, off-center, multi-component and disturbed. That means the old narrative, where galaxies spend billions of years calmly settling into disks and only later build big bulges and complex structure, is too simple. It looks more like this. Some galaxies manage to form disks relatively quickly, maybe because their merger histories are quieter or their gas inflow is smoother. Others grow fast through violent processes, like frequent mergers and intense inflows, and never have a chance to look tidy in the early phase. By the time they're already massive, they still look chaotic. The idea that morphology equals age breaks down. You can't just look at a galaxy's shape and assume you know how far along it is. And there's another important layer that JWST adds. It can show you not just the hot young stars that dominate ultraviolet light, but also the older, redder stars that dominate the rest frame optical light. At high redshift, that rest frame optical light is shifted into the near-infrared, exactly where JWST is strongest. So you can compare how a galaxy looks in UV-like filters and in optical-like filters, which basically lets you compare where the young stars are versus where most of the mass is. Sometimes the UV view looks like pure chaos, scattered bright patches everywhere. But when you switch to the rest frame optical, you see a more centralized or smoother structure underneath. In those cases, what looks messy is mainly the distribution of current star formation, not necessarily the whole mass layout. Other times, both the UV and the optical views agree that the galaxy really is physically irregular, with mass and star formation both clumped and off-center. So the mess can either be a skin-deep effect from where new stars are forming, or a sign of a genuinely unrelaxed system. That raises a key question. If the shapes are confusing, what does the motion of the stars and gas look like? Is everything just randomly moving around, or is there hidden order under the visual chaos? Early integral field spectroscopy with JWST and other instruments starts to answer that. In some high redshift galaxies, when you map how gas is moving across the galaxy, you see a pattern that looks like rotation. One side is moving toward you, the other side is moving away in a smooth gradient. That is exactly what you expect from a rotating disk, even if the image looks clumpy. In other systems, the motions are dominated by turbulence. Velocities are high in all directions, with no clear rotational pattern. Those galaxies are called dispersion-dominated, meaning random motions are stronger than ordered rotation. The tension here is important. The light can look chaotic while the motion is actually organized, or the light can look somewhat regular while the gas is still highly turbulent. The two don't always match in an intuitive way, and that means you need both imaging and kinematics to really understand what stage a galaxy is in. Then there's the question of environment. JWST is showing that some of the most massive early galaxies sit in overdense regions, the crowded city blocks you heard about earlier. Those galaxies often have complex, disturbed structures, probably because they're sitting where mergers and interactions are most common. Gravity in those dense environments pulls in gas and smaller galaxies from many directions, constantly disturbing whatever ordered structure tries to form. In quieter regions, where the environment is less crowded, you might get more time for a disk to form and stabilize. So you start to see a pattern. Morphology, mass, and environment are linked from very early times. A big, massive galaxy in a dense environment might still look messy, because it grew through repeated mergers and intense inflows. A smaller galaxy in a quieter neighborhood might already show a disk, because it was allowed to evolve more gently. The traditional Hubble sequence, the nice diagram of ellipticals, spirals, and irregulars that works well for nearby galaxies, doesn't capture this wild early period very well. Out there, the categories are blurred, and the path from one type to another is not a straight, slow line. What JWST is really doing here is breaking the simple idea that structure always lags behind growth. You can have a galaxy that is already grown up in terms of mass and star formation history, but still looks visually chaotic. You can have rotation buried inside a clumpy light profile. You can have environment driving weird shapes very early. That's why just looking isn't enough anymore. You need to connect appearance, motion, chemistry, and surroundings to get the real picture. And once you accept that, you're pushed to a new level of detail. If the global shapes and motions are this complex, what about the small-scale regions inside these galaxies, the individual pockets where stars are actually forming? JWST is sharp enough to zoom in on star-forming clumps and regions inside both nearby and distant galaxies. The next step is to ask, what do those nurseries look like up close? And can you use nearby examples as a key to decode the unresolved tiny regions in the high-redshift galaxies you can't fully resolve yet? You're not just counting galaxies anymore, you're looking inside them. JWST is zooming into their guts, separating individual star-forming regions and showing you what the actual birthplaces of stars look like, both nearby and, in a rougher way, in the early universe. That's important, because if you want to understand what distant baby galaxies are doing, you need to know what a real star factory looks like up close. So how do you get that close-up view? You start with nearby galaxies where JWST can actually resolve individual regions instead of just seeing one blended blob. Take objects like NGC 628, a face-on spiral, or NGC 1365, a barred spiral. In those systems, JWST can pick out separate pockets of star formation in the infrared. You see knots along the spiral arms, clusters in the central bar, and small clumps in the outer disk. Each of those regions is its own mini laboratory, with its own age, gas density, and dust content. These nearby galaxies act as Rosetta stones. You can measure how bright a single star-forming region is, how much gas it contains, how much dust is around it, and how its spectrum looks at JWST wavelengths. Then, when you look at a distant galaxy where you can't resolve those regions individually, you can compare its total light to the patterns you saw in the nearby cases. That lets you say, okay, this distant galaxy probably has this many active regions with properties like the ones we've studied locally. But how small and intense are these regions really? JWST is showing you that some star-forming clumps are only a few hundred light-years across, and yet are forming stars at very high rates. For comparison, a typical giant molecular cloud in the Milky Way might be tens of light-years across and form stars at a much slower pace. In these compact clumps, you're packing far more mass and activity into a relatively small volume. The surface density of star formation inside them is much higher than in typical Milky Way clouds. That means the gas is denser, the pressures are higher, and the timescales are shorter. Stars don't take leisurely amounts of time to form, they're collapsing out of the gas quickly. When you then see similar clumpy structures, even if unresolved in high-redshift galaxies, you can infer that their internal star-forming regions might be even more extreme versions of these compact clumps, because those early galaxies as a whole are smaller and more active. Another key point is that a lot of the youngest stars are completely hidden in visible light. They're still wrapped in the dusty gas clouds they formed in. Optical telescopes see those zones as dark patches or faint regions. JWST changes that because it looks in the infrared, where the dust that blocks visible light becomes more transparent. Suddenly, regions that looked empty or dark in previous images light up with embedded protostars and young clusters. This is why infrared vision is critical. If you rely only on visible light, you seriously underestimate how much star formation is happening in heavily obscured regions. With JWST, you see right through much of that dust and pick up the glow from warm dust and young stars directly. That gives you a much more complete census of star formation in a galaxy. It also helps you understand how newborn stars interact with their birth clouds, how quickly they blow holes in them, and how that process scales with the overall intensity of star formation. Now, why does it matter what kinds of stars are forming, not just how many? Because the distribution of stellar masses at birth, the initial mass function, controls almost everything else: how many ionizing photons you get, how many supernovae you get, how much metal and dust you produce, and even how many black hole seeds you create. By measuring the brightness, colours, and spectra of young clusters resolved by JWST, astronomers can test whether some environments favour more massive stars than others. If you find that in extreme regions the clusters are dominated by very massive stars, more than you'd expect from the standard distribution seen in the Milky Way, that points toward a top-heavy initial mass function. That would mean, per unit mass of stars formed, you get more ionizing radiation, more early supernovae, more rapid metal enrichment, and potentially more black hole remnants that can grow into bigger black holes. Those details feed back into your understanding of reionization, chemical evolution, and the black hole problem you just heard about. So how do you connect these small regions to the larger cosmic picture? You basically zoom out in stages. At the smallest scale, you have a star-forming core, a few light years across, where individual protostars are forming. Zoom out to a few hundred light years, and you see a clump, a complex of many cores and young clusters, with gas being stirred and heated by radiation and winds. Zoom out to a few thousand or tens of thousands of light years, and that clump becomes one piece of a galaxy's disk or central region. Zoom out again to hundreds of thousands of light years, and the galaxy becomes one node in a group or proto-cluster. Stretch the scale to millions of light years and beyond, and you're looking at the large-scale structure, the cosmic web, with galaxies tracing filaments and intersections. The core idea is this: the same physical processes JWST is capturing in detail in nearby galaxies, gas collapse, feedback from young stars, dust production, and cluster formation, are likely operating at much larger scales and higher intensities in the early universe. That's why these local Rosetta Stone observations matter so much. They let you anchor the physics. If you can explain the structure and spectra of individual clumps in NGC 628 or NGC 1365, you can build models that predict what an unresolved hyperactive galaxy at redshift 8 should look like in JWST's filters. Then you compare those models to the actual high redshift data and see where they fail. Every mismatch tells you what you're missing about the star-forming physics, the initial mass function, or the role of dust and feedback under extreme conditions. And once you realize that the same building blocks of star formation, dense clumps, embedded protostars, clustered feedback, are already in place and being pushed to the limit early on, you have to look at how we're actually reading all this information. JWST isn't just giving you pictures, it's giving you detailed spectra. And those spectra are what really let you turn light into numbers about motion, chemistry, density, and energy. The next step is to see how that spectroscopic time machine works when you apply it to thousands of galaxies across cosmic history. The real power of JWST is not the pretty images you see on social media, it's the spectra, those stretched out rainbows of light that let you read the universe's history line by line. An image tells you where the light is, a spectrum tells you what made that light, how fast it's moving, what it's made of, and what kind of engine is powering it. If the pictures are the movie trailer, the spectra are the full script. JWST has several ways to do spectroscopy. NIR spec is the main near-infrared spectrograph. It can take spectra of many galaxies at once, using tiny shutters that open and close like a grid, so you can read dozens or hundreds of objects in a single pointing. NIR cam, which most people know for imaging, also has a GRISM mode that spreads the light into low-resolution spectra across the field. And MIRI, the mid-infrared instrument, can do spectroscopy at longer wavelengths, where dust and molecules glow. In simple terms, you're not just seeing where the light is, you're dissecting what made it, across a huge range of wavelengths. The first thing spectroscopy gives you is distance and motion. Galaxies and gas clouds contain atoms and ions that emit light at very specific wavelengths, like sharp fingerprints. When the universe expands, those fingerprints get shifted to longer wavelengths. That shift tells you the redshift, which you then translate into how long the light has been travelling. On top of that, if gas inside a galaxy is moving toward or away from you, its lines shift slightly around that main value. So from a set of emission or absorption lines, you get both the global redshift and the internal velocities. You can see gas flowing out at hundreds or even thousands of miles per second. You can see one side of a galaxy moving toward you and the other side moving away, signalling rotation. You can measure turbulence inside star-forming regions. A tiny shift in wavelength corresponds to hundreds or thousands of miles per second of motion, and JWST can measure those shifts very precisely. But spectroscopy doesn't stop at distance and speed. The strengths and ratios of different lines tell you about the physical conditions inside the galaxy. Certain lines get stronger at higher temperatures, others depend on how dense the gas is, others depend on how many heavy elements are present. By comparing, for example, different oxygen and hydrogen lines, you can estimate electron temperature. By looking at how some lines change with density, you get a handle on how tightly packed the gas is. From that, one spectrum can give you a full set of numbers: how hot the gas is, how dense it is, how metal-rich it is, how strong the ionizing radiation is, and whether the motions are calm or chaotic. You're not just getting a pretty colour, you're getting a full diagnostic panel. For a high-redshift galaxy that is just a small blob in the image, the spectrum can reveal a whole internal weather report: hot, dense, metal-poor, or metal-rich, highly ionized with calm rotation or wild outflows. Spectra also let you directly estimate how fast a galaxy is forming stars. Certain lines, like hydrogen's H-alpha line, are produced in regions where young, massive stars ionize gas. The strength of those lines is tied to how many massive stars are present, and that links to the total star formation rate. If H-alpha is strong, and other star formation lines are strong, you know the galaxy is actively forming stars right now. If those lines are weak or missing, star formation is slower or is shut down. On top of that, you can tell whether a galaxy's energy output is dominated by stars or by a black hole. High ionization lines, from gas stripped of many electrons, often point to the presence of an active galactic nucleus. Certain line ratios are hard to produce with stars alone, but are natural around a hot accretion disk around a black hole. So by plotting these ratios, you can separate pure starbursts from systems where a central black hole is doing a significant part of the work. JWST's infrared spectra are especially good at this for high-redshift objects, where optical diagnostics are shifted out of reach for ground-based telescopes. The mid-infrared side adds yet another layer. MIRI spectra can pick up features from warm dust and complex molecules, like polycyclic aromatic hydrocarbons, which trace regions where stars are forming and dust is being processed. That helps you track how dust evolves, how star formation is distributed, and how feedback is affecting the interstellar medium. So between NARSPEC, NERACAM GRISM, and MIRI, you get a multi-wavelength, multi-tool view of what's going on inside these galaxies. Now, take that one galaxy picture and scale it up. If you get spectra for thousands of galaxies across the sky, each with a measured redshift, you can build a three-dimensional map of the universe. On the sky, you have right ascension and declination, basically the galaxy's coordinates. The redshift gives you its distance along the line of sight. Put those together and you place each galaxy in a 3D grid. Do that over and over and the pattern of the cosmic web starts to appear, not just in simulations but in the real data. You see filaments, clusters, and voids. You see where galaxies are packed together and where they are sparse. You can track how the number and type of galaxies change with redshift, which means with cosmic time. In effect, you're stacking thousands of little spectral barcodes to reconstruct how structure built up, where star formation was happening, and where black holes were growing at different epochs. This is why spectra are a time machine. Each one locks a galaxy to a specific moment in cosmic history and tells you what conditions were like there. When you put all of those moments together, in nearby galaxies, in intermediate ones, and in the earliest systems JWST can see, you get a continuous record of how the universe went from simple gas to the complex mix of galaxies, stars, black holes, dust, and heavy elements you see today. And once you can date stellar populations and measure conditions that precisely at high redshift, another pattern comes into focus. Some galaxies at early times already host stars that are not brand new. They have ages of hundreds of millions of years, which means their star formation started even earlier than the time you're observing. That compresses the allowed window for when galaxies could have formed and grown, and it forces you to rethink how quickly the universe built its first major structures. Before JWST, you could tell a simple story. Galaxies take billions of years to grow up. They slowly assemble their stars, settle down, and only much later do you see big, mature systems. Now the data is telling you something harsher. A lot of the main action seems to have happened in a brutally short window, compressed into the first few 100 million to first billion years. The universe didn't coast, it sprinted. So how do you know that? How do you actually measure when stars in a distant galaxy formed? One way is by age dating stellar populations using spectra and detailed SED modelling. When JWST looks at galaxies at redshift 7 to 10, it doesn't just measure how bright they are, it measures how their brightness changes with wavelength, and it picks up specific spectral features. Things like the strength of the so-called Balmer break, or particular absorption lines from older stars, tell you if there's a significant population that's been around for a while. When you fit those features with models of evolving stellar populations, you sometimes get ages of 100 to 200 million years or more for stars inside galaxies that you are seeing, when the universe itself is only maybe 500 to 700 million years old. That means those stars must have started forming very quickly after the Big Bang, more or less as soon as the gas had cooled enough and gravity could gather it. You're not looking at a galaxy that just turned on, you're seeing one that already has a history behind it. That alone would be enough to tighten your timeline, but JWST goes further. It doesn't only find galaxies that are still in a growth phase, it finds systems that look like they've already shut down a lot of their star formation. These are the so-called quenched or dead galaxies. Their spectra show relatively weak emission lines that would indicate ongoing star formation, but strong absorption features from older stars. Their colours and SED fits that suggest that most of their stars formed in a burst and then the formation rate dropped way down. The strange part is when and where you see them. You're talking about redshifts where, in your old picture, galaxies should still be ramping up, still building the bulk of their mass. Instead, you see objects that look like they have already done the heavy lifting and are now mostly coasting. In simple language, they are retired galaxies living in a universe that is still in kindergarten. That means not only did they form fast, they also stopped forming new stars earlier than you expected. Put these two facts together, early ages and early quenching, and you get the idea of compressed formation histories. The star formation histories you used to spread over a few billion years now have to be squeezed into the first billion years or less for some objects. Instead of a slow rise, a broad peak and a gentle decline, you might have a sharp spike, where a galaxy forms a huge fraction of its stars in a very short period, then drops off. This is like taking a 2-hour movie and compressing it into a 15-minute highlight reel. All the major events still have to happen. Gas has to fall into dark matter halos, cool, fragment into clouds, form stars, drive feedback, enrich the gas, maybe fuel a central black hole, and then somehow the whole system either stabilizes or shuts itself down. JWST is telling you that for at least some galaxies, all of that happened in a much shorter time than your older models allowed. That compression immediately feeds back into the underlying physics you thought was in control. Dark matter halos grow by merging and accreting smaller halos over time. Gas cools and falls into those halos at rates set by the density of the universe and the cooling properties of the gas. Feedback from supernovae and black holes heats and ejects gas, slowing growth. If galaxies are forming stars faster and quenching earlier, something in that chain has to be more efficient or differently tuned than you assumed. Maybe dark matter halos in some regions are assembling faster than average, creating deep potential wells early on. Maybe gas cooling is more rapid because of early metal enrichment, even at high redshift. Maybe feedback is more bursty, allowing short periods of very high efficiency before blowing everything out. Or maybe your recipes for how gas converts into stars, which were calibrated on lower redshift galaxies, simply break down in the extreme conditions of the early universe. This is exactly where theory teams are now scrambling, rerunning simulations with different star formation efficiencies, feedback strengths and initial conditions to see what it takes to match the JWST timelines. There's also the question of what this means for the standard cosmological model itself, the ЛCDM framework. ΛCDM tells you how dark matter and dark energy set the broad evolution of the universe, and on large scales, it still matches a huge amount of data very well, from the cosmic microwave background to galaxy clustering today. JWST's results don't immediately overthrow that. Most cosmologists still think the overall framework is basically right. But the small-scale baryonic physics, the behaviour of normal matter inside halos, is clearly under stress. If you need galaxies to form stars faster, enrich themselves sooner, build black holes earlier and quench in a baby universe, then your current subgrid models in simulations, the parts that describe star formation, feedback and gas flows, are probably too simple or too conservative. You might not need to throw out the universe's operating system, but the apps that handle galaxy formation definitely need an update. There are, of course, more speculative ideas on the table too. Some people ask whether slightly different dark matter properties, or early episodes of extra energy injection, or tweaks to initial conditions could help explain the speed up. These are interesting to explore, but they're not the default answer yet. The more grounded approach is first to push the known physics as far as it can reasonably go and see if that's enough. JWST is the stress test, and so far it's telling you that your old comfortable timelines were too relaxed. The bottom line is simple: the universe used its early time much more aggressively than you expected. Galaxies didn't slowly warm up into action over several billion years. Many of them seem to have turned on hard-formed stars at extreme rates, enriched themselves, sometimes fed central black holes, and even shut down, all within the first billion years. That forces you to rethink not just when things happened, but how connected those processes are. And once you realise that, you're naturally going to ask a more personal question. If galaxies everywhere were going through this compressed, intense evolution so early, what does that say about the history of your own galaxy? What did the Milky Way look like during that violent phase? And how do JWST's deep views of the distant universe double as a kind of baby photo album for the galaxy you live in now? Every time JWST looks billions of years into the past, it's basically spying on the Milky Way's baby photos, and those photos do not look like the calm, flat spiral you see in textbook images. If you want to know where your galaxy came from, you have to accept this first. The Milky Way grew up in a much rougher neighbourhood, and JWST is finally showing you what those early phases probably looked like. The trick is, you obviously can't see the actual Milky Way into the distant past, because you're sitting inside it. So instead, astronomers look for galaxies at intermediate redshifts around Z2 to 3, with masses, sizes, and star formation rates that line up with what simulations predict for the Milky Way's ancestors. These are the proto-Milky Ways, galaxies that are not identical twins, but close cousins at the right age and mass scale. When JWST and other telescopes measure them, you find systems with total stellar masses in the same rough range as what the Milky Way had at those times, and disk sizes that are a fraction of today's. But the key difference is how they behave. These proto-Milky Ways are far more turbulent and far more actively forming stars than the galaxy you live in now. Instead of 1 or 2 solar masses of new stars per year, you might be looking at tens of solar masses per year, with gas flows and clumps all over the place. Your home galaxy's past looks less like a quiet suburb and more like an overbuilt, noisy construction site. So what does the actual structure of those galaxies look like? JWST's rest frame optical views, which capture the older stellar populations and the bulk of the mass, show that many of these systems don't have thin, cold disks yet. Instead, they have thick, somewhat puffed up disks that are clumpy and irregular. You can imagine a disk, but with a lot of vertical thickness, and with massive star-forming clumps scattered through it. Those kinds of structures line up well with what we know about the Milky Way's own thick disk and bulge. In our galaxy, stars in the thick disk and in the central bulge tend to be older and more metal-rich than many thin disk stars, and their orbits are more tilted and random. Their ages point back to a time when the Milky Way was still in that turbulent, high-activity phase. So when JWST shows you a thick, clumpy disk at Z2, you're likely looking at the same type of environment that built the thick disk and bulge you see in the Milky Way today. But structure alone doesn't finish the story. You also need to ask how the Milky Way gained all that mass. JWST's view of proto-Milky Ways, combined with simulations, points to 2 main channels: smooth gas accretion from the cosmic web and merges with smaller galaxies. Gas from intergalactic filaments flows into the galaxy's dark matter halo, cools, and feeds new star formation. On top of that, smaller satellites fall in, get distorted, and eventually dissolve into the larger system. You can see the fossil evidence for this in your own galaxy's stellar halo, the extended faint population of stars surrounding the Milky Way. Surveys like Gaia have mapped out streams and groups of halo stars with shared motions and chemical fingerprints, showing that some came from past mergers with dwarf galaxies. JWST's images of high-redshift galaxies, with their tidal tails and interacting companions, look like the earlier versions of those same events. The violent accretion history that simulations predict and that Gaia records in our halo matches the kind of action JWST is catching in similar mass galaxies far away. Now tie that to chemistry. JWST is measuring the chemical enrichment of galaxies at many stages, including those proto-Milky Way systems. You see how fast elements like oxygen, magnesium and iron build up in their gas and stars. When you compare that to detailed measurements of old stars in the Milky Way, especially in the thick disk and halo, you see similar patterns, rapid early enrichment, then a change in the relative amounts of different elements as the star formation rate evolves. This is what people mean by galactic archaeology. You use old stars in the Milky Way, with their detailed chemical abundances, as time capsules. At the same time, you use JWST to look at external galaxies at earlier cosmic times, and you compare their global chemical properties to the fossil record inside our own galaxy. You're using galaxies across billions of light years like mirrors to reconstruct our own past. If the abundance patterns match, it's strong evidence that the Milky Way really did go through phases similar to what JWST is seeing in those distant systems. So where do you fit in this whole history? The Sun is about 4.6 billion years old. By the time it formed, most of the Milky Way's wild youth was already over. The thick disk and bulge were largely in place. The most violent merger events had already happened, and the galaxy had started to settle into a more ordered, thin disk. That's the structure the Sun was born into. The calm spiral arms you see in long exposure photos today are the end result of that chaotic early period, not the state the galaxy was in when it was first building itself. In other words, you live in the after picture. When you look up at the Milky Way on a dark night, you're seeing a system that has already gone through intense starbursts, violent mergers, rapid chemical enrichment, and strong black hole and supernova feedback. JWST's deep views of other galaxies at earlier times are the before and during shots. Put them together, and the Milky Way stops being a static backdrop and becomes what it really is, one outcome of a fast, messy, competitive growth process that played out across the universe. And once you see your home galaxy that way, as just one product of that compressed high-pressure early environment, you circle back to the bigger question. If this is what it took just to build something as normal as the Milky Way, what does that say about the standard cosmological model itself? Can the usual ΛCDM framework really handle this much early structure, this many massive galaxies, this much rapid growth without breaking? Or are we reaching the point where the underlying model starts to feel the strain? Every new ultra-deep image, every new spectrum from JWST is basically an exam for the standard cosmological model ΛCDM. So far, the model is bending to accommodate what we're seeing, but the obvious question hanging over all of this is simple. How close are you to the point where it stops bending and starts breaking? Start with the cleanest test. How many bright galaxies exist at very high redshift compared to what big cosmological simulations predicted before JWST? Those simulations, based on ΛCDM, tell you how dark matter structures should grow and how many halos of different masses you should get at different times. Then you plug in recipes for how gas turns into stars, and you get forecasts for how many galaxies of a given brightness should exist at, say, redshift 10 and above. When JWST looked that far back, especially in deep surveys, it found more bright galaxies than many of those forecasts expected, particularly at the high luminosity, high mass end. Instead of a slow thinning out of bright galaxies as you go to earlier times, the drop-off is not as steep as you thought. You're counting more big active systems in a universe that is only a few 100 million years old. That's the first point of tension. The observed galaxy abundance at high redshift, especially for the massive ones, overshoots some of the pre-JWST curves. Now, bright galaxies imply a lot of stars, and a lot of stars imply a deep dark matter potential well underneath. You can't build a massive galaxy without a massive halo, so if the galaxies are really as heavy as they look, then their host halos also have to be heavy and in place early. That sends you back to the dark matter side of the calculation. The halo mass function, which tells you how many halos of a given mass exist at a given time, comes straight out of ΛCDM. At very early times, the number of massive halos is supposed to be low, because structures haven't had many chances to merge and grow. If JWST is seeing more massive galaxies than there are predicted massive halos to host them, that's a serious mismatch. Some of this can be eased by uncertainties in how you infer mass from light, or by the fact that most simulations have limited volume and might undersample rare objects. But if the discrepancy holds up even after accounting for those uncertainties, it means either that you underestimated how quickly halos can assemble at high redshift, or that the galaxies inside those halos are more efficient at turning gas into stars than you assumed. That leads to the first and most conservative response from theory: retune the galaxy formation knobs without touching LCDM itself. You can increase star formation efficiency in early halos, meaning that a larger fraction of the available gas is converted into stars in a given time. You can modify feedback prescriptions, changing how strongly supernovae and black holes blow gas out of galaxies. Maybe in the early universe, feedback was less effective at stopping star formation, or acted in shorter, more intense bursts. In practical terms, you're taking the subgrid physics in simulations, the parts that describe star formation and feedback on scales too small to resolve directly, and pushing them toward their limits to see if you can match the JWST counts. You're asking if we make galaxies as efficient as reasonably possible. Given what we know from nearby systems and basic physics, can we produce enough bright, massive galaxies at high redshift? You're pushing the knobs in the simulations to their edge to match JWST. If that works, then ΛCDM survives, but with a clear message: your previous assumptions about early galaxy physics were too conservative. If it doesn't work, or if it only works by choosing parameter values that look unrealistic when compared to other data, then you're pushed to consider more radical possibilities. That's where alternative ideas come in, carefully. Some researchers explore non-standard dark matter, like particles that interact slightly with each other, or have different velocity distributions, which could change how quickly small structures grow. Others look at early dark energy, a brief phase where dark energy behaved differently and altered the growth of fluctuations. There are also proposals to tweak the initial conditions, like allowing slightly more power on small scales in the early density fluctuations. All of these could, in principle, help create massive halos earlier, but it's important to keep this grounded. These ideas are speculative. They're not established replacements for ΛCDM, and they have to pass a lot of other tests, like matching the cosmic microwave background and large-scale structure at later times. You're not at the point where you can say the model is broken. You're at the point where JWST is a serious stress test, and some parts of the model's implementation, the details of galaxy formation and possibly small-scale structure, are under heavy pressure. What you're watching right now is the scientific process in real time. Observers push JWST to its limits, find galaxies earlier, brighter and more complex than expected, and publish those results. Theorists take that data, update their simulations, adjust their physics, and see how close they can get. Those new models then make new predictions, for example about how common certain kinds of galaxies should be, or what their spectra should look like, at slightly different redshifts or in different environments. Then new JWST proposals are written to go look for exactly those signatures. This loop, new data, new models, new predictions, new data, is not a sign of crisis. It's exactly how cosmology is supposed to work. ΛCDM has passed many tests from the microwave background to galaxy clustering today. JWST is adding a completely new set of tests at the earliest times, where the data used to be thin. If the model survives, it comes out stronger and more tightly constrained. If parts of it fail, you learn something fundamental about dark matter, dark energy, or the initial conditions of the universe. Either way, the stakes are high, because all of this early structure and rapid growth doesn't just affect abstract cosmological parameters, it directly feeds into when and how the universe became chemically rich enough to form planets, atmospheres, and potentially life. If everything happened faster and earlier, that shifts the timeline for when rocky planets and complex molecules could exist. So the natural next step is to ask, in a universe this vast and this intense, how quickly did the ingredients for life start to appear around stars and in planetary systems? While JWST is busy rewriting the story of galaxies and black holes, it's also doing something much more personal. It's testing how common the basic ingredients for life really are, even in a universe that looks this violent and chaotic. You're not just learning how stars and galaxies form, you're learning how often nature builds atmospheres, oceans, icy grains, and complex molecules that could eventually end up on worlds like Earth. Start with exoplanets, because that's where the connection to life hits closest to home. JWST can take spectra of exoplanet atmospheres by watching a planet pass in front of and behind its star. When the planet transits, some starlight filters through its atmosphere. Different molecules absorb different wavelengths, so when you spread that light into a spectrum, you see small dips at specific colours. That's a transmission spectrum. When the planet goes behind the star, you can compare the combined light before and during the eclipse to get the planet's own thermal emission. That's an emission spectrum. With those two methods, JWST has already detected signatures of water vapour, carbon dioxide, and in some cases methane, in the atmospheres of giant exoplanets. Many of these are hot Jupiters, gas giants orbiting extremely close to their stars, with temperatures of a few thousand degrees Fahrenheit. They are not habitable in any normal sense. They're more like giant blast furnaces. But the point is that the chemistry you care about, molecules with hydrogen, carbon, oxygen, is showing up clearly in the data. JWST is proving that its infrared vision can pick out these molecules even when the planet is just a tiny fraction of the star's brightness. Next, move closer to the actual birthplaces of planets, the disks of gas and dust around young stars. JWST looks at these protoplanetary disks in the infrared and sees not just generic dust, but specific features from icy grains and organic molecules. You see hints of water ice, carbon-bearing compounds, and more complex species in the cold outer regions of the disks, along with warm dust closer in. These disks are basically the raw material for future planetary systems, the stuff that will clump and collide to form rocky planets, gas giants, asteroids and comets. What matters here is the link back to the big picture story of metals and dust. Those ices and organics don't appear in a vacuum. They need heavy elements like oxygen, carbon, nitrogen, and others that were forged in earlier generations of stars. When JWST sees rich chemistry in disks around young stars, it's seeing the local result of the same cosmic metal enrichment you've been hearing about at galaxy scales. The faster galaxies enrich themselves with heavy elements and dust. The sooner disks like these can form with the right ingredients for complex chemistry. Then look at star-forming regions themselves, the dense clouds where both stars and their disks form. In places like the Orion Nebula, which JWST can observe in incredible detail, you're seeing the same kind of environment that existed in older galaxies, but at a distance where you can resolve individual structures. JWST's infrared data shows that these regions are full of complex organic molecules, not just simple gas. You see emissions from carbon-based molecules, ices coating dust grains, and structures shaped by radiation from nearby massive stars. These regions act like chemical laboratories. Ultraviolet radiation, shocks, and dust grains all work together to build and process molecules, sometimes breaking them apart, sometimes building larger ones. The important point is that many of the ingredients you associate with prebiotic chemistry are being formed in generic star-forming clouds. These are the same kinds of clouds that, in earlier epochs of the universe, sat inside the galaxies JWST is seeing at high redshift. So what you learn locally about chemistry in places like Orion can be applied to those distant, unresolved star-forming regions that you can't zoom into as clearly. Now, connect that to the timeline. Earlier, you saw that galaxies in the young universe became chemically enriched much faster than expected. They built up heavy elements and dust in a few 100 million years to 1 billion years. Heavy elements are required for rocky planets. You need silicon, oxygen, magnesium, iron and other metals to build solid surfaces. You need carbon, nitrogen and oxygen to build complex molecules in atmospheres and oceans. If those elements are present early, then, in principle, rocky planets and complex chemistry could also appear earlier than you thought. So you have to ask a straightforward question: could habitable planets have existed when the universe was only a few billion years old, instead of needing most of cosmic time? If galaxies were already rich in metals, already forming second and third generations of stars with protoplanetary disks, then there's nothing in basic physics that forbids terrestrial planets and stable orbits at those times. We don't know how common truly habitable worlds were back then, or whether life had enough time to start, but JWST is pushing the minimum time when the raw materials were available downward. Exoplanet atmosphere surveys will push that further. If JWST and follow-up missions start finding Earth-sized or super-Earth-sized planets with atmospheres that show signs of water and carbon-bearing molecules around relatively old stars, that will tighten the picture. Even now, JWST is testing whether smaller, cooler planets have thick atmospheres or if they've been stripped. That matters because it tells you how often planets keep their gases long enough for interesting chemistry to run. All of this changes how you think about your place in the universe. You're not just on Earth, in the solar system, in the Milky Way. You're in a universe where the ingredients for life, heavy elements, dust, ices, complex organics, were being brewed early and often across many galaxies over most of cosmic history. The same physical processes that build giant clusters and fuel black holes also set the stage for small rocky worlds with thin atmospheres and liquid water. JWST's role here is to tie those scales together. The same telescope that shows you an overmassive galaxy 500 million years after the Big Bang is also taking spectra of a hot Jupiter's atmosphere and imaging a disk around a young star. That means the search for life is no longer a separate story from galaxy formation and cosmology. It's part of the same chain. You go from dark matter halos to gas collapse to star formation to metal production, to disk chemistry, to planets, to atmospheres, and maybe eventually to biology. And that brings you to the final step in this whole journey. After everything JWST has shown you, fast galaxy growth, early black holes, rapid enrichment, extreme star formation, possible early planets, you have to update the big narrative. The old picture of a slow, simple, empty early universe is gone. The new picture is fast, crowded, dusty, chemically rich, and already weird almost from the beginning. The question now is, how do you pull all of this together into a new cosmic story that still keeps what works from the old model, but fully reflects how intense the early universe really was? By the time you add up everything JWST is showing you, the old story of a slow, simple, mostly empty early universe is just gone. The new picture is a universe that starts fast, packs itself with structure early, fills itself with dust and heavy elements quickly, grows black holes too big too soon, and runs star formation at rates that look almost unreasonable. The quiet, gentle origin story you might have had in your head has been replaced by something much more intense. Think about the main shocks. First, you have massive galaxies showing up a few 100 million years after the Big Bang, with billions of solar masses in stars, when standard models said you should mostly see small growing systems. On top of that, some of those galaxies already host actively feeding black holes that are far from tiny. Then you see rapid metal enrichment and dust building up early, which tells you that multiple generations of stars have already formed and died in a short window. Add in extreme starbursts in compact volumes, with tens or hundreds of suns worth of gas turning into stars every year, in regions only a fraction of the Milky Way's size. All of that points to a young universe that is busy, not empty, aggressive, not slow. Before JWST, the mental image for many people was simple. Dark matter halos grow slowly, small galaxies appear, then gradually merge and build up, with star formation and chemical enrichment ramping up over billions of years. There was structure, but it was supposed to be modest at very early times. Now the observations are forcing you to replace that with a different picture. Structure, star formation, black hole growth, and metal production all kick in hard and early. You still get to the same late-time universe, but the route is more compressed, more chaotic, and far more extreme. At the same time, it's important to be clear about what has not changed. The overall framework of modern cosmology still works. The universe is still expanding, the Big Bang model still explains the cosmic microwave background, the abundance of light elements, and the large-scale structure on huge scales. The ΛCDM model, with cold dark matter and dark energy, still fits a wide range of observations extremely well from the early universe to the present day. What JWST is shaking up is not the existence of the Big Bang or the general shape of cosmic history. It's the detailed script of how structure and complexity emerged on galaxy scales. The theory of how gas in halos becomes galaxies with stars, black holes, dust and metals is where things are being rewritten. The broad strokes are solid, but the small-scale physics, the timelines, and the efficiency of the process clearly need serious updating. JWST has also created a list of open problems that are not solved yet. They were just better defined. How exactly do massive galaxies assemble so much stellar mass so fast without violating what you know about dark matter and gas physics? What is the real origin of the earliest supermassive black holes? Are their seeds mostly from massive stars, from direct collapse, or a mix? And how often do they manage to grow above their expected limits? What are the exact sources that drove reionization? How much came from normal star-forming galaxies? How much from rare, bright quasars? And how patchy was the process in space and time? You also still need to pin down how common early quenching is. How many galaxies in the baby universe already shut down star formation and why? Is it mostly feedback from stars and black holes? Or is it driven by environment, like running out of fresh cold gas in certain regions? And you need to understand how all these pieces, starbursts, black holes, dust, metals, mergers, fit together into a single consistent picture that works from the first few 100 million years all the way to galaxies like the Milky Way now. Those are the to-do list items for the next decade. On the theory side, the response is already underway. Supercomputer simulations are being retooled to match JWST's data. Codes that used to be tuned mainly to reproduce galaxies at low and intermediate redshift are now being pushed to reproduce high redshift counts, masses, metallicities and black hole populations. That means trying different star formation efficiencies, different feedback strengths, different treatments of gas cooling and mixing, and checking which combinations can produce something like the JWST universe without breaking everything else. On the observation side, JWST is not the end of the line. It's the start of a new phase. The Roman Space Telescope will survey huge areas of the sky in the infrared, giving you the big picture statistics that complement JWST's deep, narrow fields. On the ground, extremely large telescopes with mirrors tens of meters across will take high-resolution spectra of faint objects, letting you measure motions and chemistry in even more detail. Together, these instruments will either confirm that ΛCDM plus upgraded galaxy physics can handle the early universe, or they'll push the tension to the point where something more fundamental has to change. So where does that leave you, personally, when you look up? Before JWST, you might have thought of the night sky as the calm surface of a very long, very slow story, where galaxies took their time and complexity crept in gradually. After JWST, you know that is not how it went. The universe went from almost no structure to massive, dusty, chemically rich star-forming galaxies and to big black holes in a fraction of its total lifetime. It went from nothing to way more than you expected on a timescale that should have been impossible until the data forced you to accept that it happened. Now, when you stand outside at night and see the Milky Way, you're not looking at the product of a gentle evolution. You're seeing the quiet end state of a system that was built through rapid growth, violent mergers, extreme starbursts, and fast chemical enrichment in a cosmos that was already crowded and active almost from the beginning. JWST took what looked like an empty early universe and showed you it was full of action you simply hadn't been able to see. And this is the real shift. The search for how galaxies form, how black holes grow, and how the ingredients for life appear is not a set of separate stories anymore. They're all parts of one compressed timeline, one high-energy origin story that runs much faster than you thought. When you look up now, you're not staring into a slow, sleepy past. You're looking into a universe that proved very early on that it could build almost everything you see today in a fraction of the time you once thought it needed. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.